Hello everyone, welcome to my self-introduction and paper report. My name is Tran Minh Quan, but you can call me Harry here. About the content of my presentation, first I will introduce myself, second is my background, and paper report will including introduction, material and method, result and conclusion. So I was born in Ho Chi Minh City, but the local refer calling it Saigon. It's a big city in Vietnam, a Southeast Asia country. So my birthday was 2001, November 11. Some favorite activities for me is running and food explore. Talk a little bit about Saigon. You can easily find some very famous food in Saigon like pho, a beef noodle, a Vietnamese beef noodle, or banh mi with milk coffee. Some famous location you can find it here like the Walking Street, the Notre Dame in the center of Saigon. For my background is for undergrad times I was studying in IUH, Industrial University of Ho Chi Minh City, which is a sister university to CYCU. I was studying in chemical engineering, and my research field is material and wastewater treatment. For master degree, I studying in Trung Nguyen Christian University, Department of Biomedical Engineering, and my research field is biomaterial and tissue regeneration. I was working in lab 802, the Frontier Material Lab. Report. So my paper was published in 2020s. The title is Development of Double Porous PCl chitosan polymer as a Tissue Engineering Scaffold. So the paper was published in a journal name is Material Science and Engineering C with Q1 ranking and impact factor is 7.328. The introduction of the paper mentioned about tissue engineering and how scaffolding material play a crucial role in the tissue regeneration. So tissue engineering rely on porous scaffold material, integrate with cell or molecule to regenerate tissue. But scaffold material should offer specific functionality, including control over cell growth, material composition control, biocompatibility, cell enhancement, and biodegradability. But synthetic polymer like PCl, PLA, PLGA, or polyurethane are commonly used for vascular graft due to their mechanical strength, biocompatibility. However, synthetic polymer lack reactive functional site for biofunctional modification, leading to a development of a new hybrid material with natural polymer such as chitosan, like we used in this study. So chitosan is biocompatible, hydrophilic, and non-toxic, all that will providing a favorable environment for cell attachment. So blending chitosan with synthetic polymer can improve mechanical properties and degradation rate. Not only that, we can improve bioactivities to the material. So poor chitosan is mechanically weak, so blending with PCl will improve processing. The membrane were fabricated from PCl chitosan blend with modified liquid induced phase inversion technique in order to create a macro void in the surface. About the synthesis method, first membrane were made by dissolving PCl and chitosan into a solvent mixture of formic acid and acetic acid, casting them onto a glass plate. A track edge membrane filled with pores with a solvent mixture. Plate were immersed in the sodium hydroxide solution, forming membrane in minute 2 hours. This result in two structures, a single porous structure with open pore on top surface, and a double porous structure with interconnected microspore. The membrane were washed and then stored in ultra-pure water at 4 degrees. The viscosity of pure chitosan were significantly higher than the pure PCl in common solvent due to several factors. Chitosan higher molecular weight, about 190 kDa to 310 kDa compared to poor PCl around 80 kDa, and its stronger affinity toward the solvent attributes to a stronger secondary interaction. With increased viscosity, in contrast, the viscosity of PCl in acidic solvent could decrease due to the breakdown of ester linkage and reduction in polymer change, highlighting the substantial difference in solution viscosity between two polymers. Next will be the result part of the study, which will include material characterizations, degradation study, and cell biocompatibility. For material characterized, first the table right here will show us the different parameters when you're changing the ratio between PCl and chitosan. For example, some very important parameters like microvoid diameters, micropores diameters, surface porosity. So to make it clear, we have a SEM image here. So AB is poor PCl, CD is 90% PCl, EF is 80%, GH is 70%, and IJ or 100 a poor chitosan. So the SEM analysis of the membrane reveal a double porosity structure with microvoids opening towards to the top surface and interconnected with the punchy microspore network. Increasing the chitosan weights led to larger microvoid. The microvoid had diameters ranging from 20s to 90s micrometers, while interconnected microspore were around 7 micrometers, except for the PCl chitosan with the ratio 70-30, which have a micropore diameters of 20s micrometers. You can observe all the parameters in this table. For the next characterize of the material, the ATR-FTYR spectra of the PCl chitosan scaffold show distinct color representations for different composition and surface. On the bottom surface, PCl, poor PCl is in red. The PCl chitosan with ratio 90-10 is in green, 80-20 is in purple, 70-30 in blue, and the poor chitosan is in cyan. Shown on the top and the bottom surface of the same membrane. The FTYR spectra of the membrane bottom surface show characteristics matching with past report value. In crude chitosan, report peaks at 5064 indicate intramolecular hydrogen bonding between a nitrogen and hydrogen and between oxygens and hydrogen, with the peaks at 2AA0 for asymmetric bending of a CH group. The PCl exhibit peaks at 2946 and 1726, representing the CH and ester carbonyl group representative. In the PCl and chitosan blends, as the chitosan proportion decrease, the bonding between nitrogen and hydrogen and between oxygen and hydrogen stretching vibration will shift to a higher wave number. That will indicating the interaction between the two polymers with covalent bonding, which is a very strong bonding. The characteristic peaks shift by changing the compositions, suggesting the secondary interaction between the functional group of the polymer and no phase separation occur. The ATR-FTYR spectral comparisons of both sides in the same plane membrane show almost homogeneous blending homogeneous blending in the material with the ratio is 90-10 and 80-20, with the similar intensities of PCl and chitosan bands of the both surface. However, in the PCl chitosan with ratio 70-30, higher chitosan characteristic peaks on the bottom surface suggest possible phase separation through the membrane thickness. Overall, while no phase separations occur due to the interaction between the PCl and chitosan, separation could occur in the material with the ratio 70-30 due to their distinct chemical properties. The FTIR chemical mappings on either side of the membrane also be performed. The chemical mapping of the PCl cation planes on either surface on the same membrane where ester carbonide group for PCl observed at 1726 and hydrogen bond between nitrogen and oxygens observed at 3364. Red and blue color indicate the intensity of corresponding band, high and low intensity, corresponding to high and low concentration. The ATR FTIR chemical mappings of characteristic band highlight the surface chemistry difference in the membrane. Increasing cation concentrations in the plane led to decreased ester carbonide absorbance and increased bonding between nitrogen, oxygen with hydrogen absorbance. This trend, consistent with ATR FTIR spectral comparisons, suggests no microscopic phase separation in PCl cation, but the material with ratio 90-10 and 80-20s, but possible segregation in PCl cation in ratio 70-30, where cation contents appear higher on the bottom surface. The non-homogeneous distribution of PCl and cation at the micrometer scale on the bottom surface of the PCl cation 70-30 further indicate the segregation, like I mentioned before. For the crystalline and thermal properties of the material, the XRD and DAST were used. The plane crystalline properties were analyzed on the 1 cm square membrane in material with PCl cation with ratio 80-20 and 70-30. Cation pore peaks at 19 degrees indicate its amorphous nature. And about the PCl, PCl will show the intense peak at 21.5 and 23.5 degrees. That will corresponding to 110 and 200 planes. Increasing cation contents likely increase the PCl peaks angle, suggesting the interactions. And surprisingly, the PCl peaks intensity increase with more cation. This will indicate the enhanced crystallizations. Other peaks suggest different crystal with the planes contribute to overall crystalline behavior. However, in the material with 70-30 ratio, show almost no peaks, indicating significant amorphousness due to cation. About the DSC, the DSC analyses were performed on the sample patch to investigate the plane behavior. Generally, a higher polymer material crystallinity requires more energy to break the crystal, resulting in a higher melting temperature, or TM. In this study, increasing the weight percentage of the cation leads to increase in the plane, except for the BCl cation with ratio 70-30 ratio, where it decreased. The phenomenon is closely linked to the plane crystallinity, as discussed earlier. Poor PCl typically melts at 60 degrees, while cation degrades at around a very high temperature, 270 degrees before melting. Determining the class transition or TT of the cation using conventional thermal technique remained challenging despite some effort. Therefore, the study monitored the variation of PCl melting point in the planes by altering the composition of cation. Contrary to some report data, the study found to increase the cation weight percent generally will increase the plane TM, except for the PCl cation with 70-30 ratio, where it's decreased. To design a desired biomaterial for tissue engineering application, the degradation is very important to study. So we got the weight loss were calculated by the following equation and can be seen in Fig A and Fig C. For Fig A is the weight loss of the sample with the lipase enzyme. In here is the Pseudomonas capacia. The effect of the enzymatic degradation by lipase on the sample show a rapid and selective degradation of PCl. PCl within the 48 hours due to the high enzyme concentration, used, which is 7 U per milliliters, which is significantly higher than the physiological condition. The enzyme could easily diffuse through the porous scaffold, leading to the faster degradation compared to non-porous scaffold. And for fixie is the weight loss of the sample without the enzyme after 90 days. When the degradation was conducted without the enzyme, the degradation of the plant was significantly low. Moreover, per PCL showed the lowest degradation, and the degradation increased with increasing the catechol weight percent. For FIC-P, it's the pH of the enzyme degraded solution after the study. The pH of the degraded solution remained close to the physiological pH, which is around 7.4 in all plants, indicating minimal toxicity. The poor catechol had the lowest pH, likely due to the higher amount of acidic residue from ester chain degradation. The surface morphology of a degraded membrane after a different time interval is present in this figure. The SEM image taken at different time points during the enzymatic degradation of PCL catechol material plants provide a comprehensive view of the degradation forces. Here, first we have the 6 hour. This image likely captured the initial state of degradation. We're showing the early sign of structural alterations and surface modification induced by lipase activities. After that is the 1 day. Image at this day, 1 day, may reveal some advanced structural change and surface erosion, providing insight into the progression of degradation over a short period. At 10 days, SEM image taken after 10 days can show significantly degradation effect, illustrating extensive structural modification and surface degradation pattern can have developed over a long period. And without the enzyme, for 90 days, the image served as a control, showing the long-term stability and structural integrity of the plant over the extended period in the absence of the enzymatic activities. This will highlighting the inherent degradation resistance of the PCL catechol plant material. Next, for the macroscopic morphological structurations of the membrane, the phase diagram illustrates the membrane formation process in a ternary system of polymer solvent, non-solvent, guiding the road through double porosity. Point within the triangle represent the mixture into two phases. One phase regions are mixable, while two phase regions separate into high viscosity or polymer rich and low viscosity or polymer poor phases. The liquid-liquid phase boundary is the polynomial curve, where compositions inside be mixed into two phases in equilibrium. The tight line connects the equilibrium compositions. At low polymer concentrations, the system is a low viscosity polymer poor phase, and polymer concentration increase, viscosity rise rapidly, reaching the chelation point E, where polymer change movement stops. The membrane formation path ABCD starts at the initial cast solution A and process to demixing B, solidification C, and final structure is D. The positions of point D on the polymer non-solvent line determine overall porosity. The presence on the track edge membrane restricts the non-solvent excess, initiating a biaxially heterogeneous solvent-non-solvent exchange, resulting in macrovoid formation. The polymer plant composition, polymer weight percent, and non-solvent concentrations improve the macrovoid size and membrane porosity. Another important study is for the material is the cellular compatibility. The cellular compatibility of the membrane were assessed using HUVEX. After 3 days, conventional image show high cell adhesion on all membrane, with PCL catechol plants inhibiting even higher cell interaction and forming almost confluent monolayers within 3 days. STX magnification, cells maintain their endothelial-like morphology, particularly in BCL catasan with ratio 80-20 and 70-30 blends. This result indicating a high biocompatibility possible due to their improving hydrophilicity, pore spacing, and morphology with catasan. Studies have shown rapid cell enhancement and proliferation on BCL catasan scaffold due to higher VEGF absorptions on the catasan-rich side. This will highlighting the potential of this plant for tissue engineering application. The cellular characterizations of this double porous material was conducted with HMSC and HUVEX, showing good cellular invasion and proliferation with increasing catasan weight %. The material also exhibits a 10 hydraulic resistance, suggesting improved cellular barrier function. These findings are significant for developing a bioscaffold construct for small diameter blood vessel regeneration. NSC can be seeded into the scaffold to reduce VEGF and differentiate into smooth muscle cell, while EC can be seen on the luminal side to regenerate the endothelium. As cell grows, the scaffold is gradually replaced, eventually being absorbed by the body to form a blood vessel construct. For the conclusion, this study has developing a BCL catasan membrane with unique double porosity for tissue engineering, fabricate using a modified phase inversion technique, inhibiting microvoids and connect through a microporous network. For the method, solvent optimization, polymer blending, and membrane formation were detailed. And the membrane exhibits a unique double porosity level with microvoid and microporous network. The membrane structure supports a cell enhancement, proliferations, and nutrient transfer, making it suitable for tissue repair application. For the collusion for characteristic of the material, the ATR-FTYR confirms secondary interaction between BCL and catasan, with slight polymer saturation at high catasan weight %. XRD and DSC study indicate the increased crystallinity and melting point with higher catasan weight %. Biodegradability adjustable by varying BCL catasan ratio, with enzymatic degradation showing selective BCL degradation. HUVEX demonstrate rapid enhancement and proliferations, maintain natural morphology, suggesting potential for vascular graft application in tissue engineering. Thank you everyone for listening to my self-introductions and paper report today. If you have any question, just comment down below. I will try my best to answer to all of you. Thank you so much.